In the last class, we were discussing about the this topic that was like this continuous time Fourier transform. So today we'll start with the continuous time Fourier transform in the system domain. So for a system, what is the usefulness of this Fourier transform? So let me open it here. So here in the Laplace also we have seen that whenever we have a time domain signal or time domain system, and when we transform into the Fourier Laplace domain or the Fourier domain, the calculation becomes much easier. So again, in this case, we have an input signal xt and impulse response ht and output yt, and when we take its Fourier transform, it will be x of omega. For this one, it will be h of omega, and for this one, it will be y of omega. And we know that the output is given as a convolution of this ht with x of t, and in the frequency domain, it will become y of omega equal to x of omega, h of omega. Okay. Again, this h of omega, what we call it as a transfer function. So this one is known as a transfer function of a system. Okay. And this is the input, and this is the input, this is the output. So h of omega will be given as y of omega and x of omega. In the Laplace also we saw similar thing, that h of s was equal to y of s divided by x of s. Now this h of omega has some different use as compared to this Laplace, so I will go through that now. So this filters that we design for the system, like a low pass filter, high pass filter, and band pass filter, all these filter are generally represented with the help of this h of omega in the frequency domain. Okay. So first filter is the ideal low pass filter. So the ideal low pass filter is going to pass the low frequency signal, and it is going to reject the high frequency signal. Okay. So this is how the response of the ideal low pass filter going to look like. Okay. This omega c, we call it as a cutoff frequency, meaning that this is the frequency below which the signal will pass all the signal, and if this input signal is more than this frequency, this filter is going to reject those kind of signal. Now, let me give you one example. Let's say we have a filter which is given by this transfer function. Okay, so it is h of omega is equal to 1 for mod of omega less than 10 pi, otherwise it is 0. So what it means is that omega c is equal to 10 pi and minus omega c is equal to minus 10 pi. So this is the filter that have been given. And let's say we are giving the input to this filter is cos 6 pi t. Okay. So this is cos 6 pi t. Now, if you see this cos 6 pi t signal, when you take its, if you calculate what kind of frequency content it has, so it will turn out that it has a content located at minus 6 pi and plus 6 pi. Okay, and this is the x of omega. So this is the h of omega, this is the x of omega. Now we know that y of omega is equal to x of omega and h of omega. Okay. Now this is the x of omega, which is equal to which is like a 2 impulse located at 6 pi and minus 6 pi. Now when you multiply this x of omega with h of omega, it is going to be same as x of omega, because h of omega is equal to 1 at omega equal to minus 6 pi and plus 6 pi. Okay. So at this two frequency, h of omega is equal to 1. Since h of omega is equal to 1, it means that y of omega will be simply equal to x of omega, because the frequency of interest here is minus 6 pi and plus 6 pi. So in this case, if you're giving the cos 6 pi t as an input, your output will also be equal to cos 6 pi t. Now let's take another example, that we have a signal which is equal to cos 24 pi t. Okay. Again, for this case, when you take the Fourier transform, cos 24 pi t, its content will be located at minus 24 pi and plus 24 pi. Okay, so there is a one impulse here, that's a one more impulse here. Now this is the x of omega, and y of omega will be given as this x of omega multiplied by this h of omega. Now if you see this h of omega is equal to 0 at 24 pi and minus 24 pi. Okay, since this h of omega is equal to 0 at this frequency of interest, the output will be equal to 0. Okay, so if this is the input, for corresponding this input, output will be equal to 0. So this is how the filter is working. It is rejecting the signal which is above the cutoff frequency, which is 10 pi here, and passing the signal which has the frequency less than the cutoff frequency. Okay. Now let me take an example in which we have a signal which is like composed of multiple signal. We have one, we have cos 24 pi t, and we have cos 4 pi t. Okay, so in this case, this one means it is a DC signal or a constant. This is DC, which means that it is a omega equal to 0. This is omega equal to minus 24 pi and plus 24 pi. Okay, and for this one, omega will be equal to 4 pi and minus 4 pi. Okay, now the cutoff frequency is 10 pi, which means that this signal will get rejected, this signal will pass through, and this signal will pass through. Okay, so if this is the input, the corresponding output will be equal to 1 plus cos 4 pi t. Okay, this 24 pi t will get rejected by this low pass filter. Anyone has any doubt? So this is how the low pass filter works. Let me go to the next filter. Next is the just opposite of low pass filter. It is known as a high pass filter. So in this case, signal will this filter will pass only those signal whose frequency is more than the cutoff frequency, and if it is less than those cutoff frequency, this filter or the system is going to block those kind of signal. Okay. So again, I have taken the similar filter, but here now it is for less than 10 pi, it is equal to 0 and 1 otherwise. Okay, it is just opposite of what we saw in the last slide. Now in this case, if you apply this signal, it will get rejected. For this one, yt will be equal to 0, because now this 6 pi t is going to fall in this range and this somewhere here, and this filter is going to reject that signal. Now this signal is going to pass through this filter, which is somewhere located here. Okay, so this in this case, yt will simply be equal to cos 24 pi t. Okay. Now in the last case, we have a DC, we have a 24 pi, and we have 4 pi. So in this case, this portion will get rejected, this portion will get rejected. So in this case, yt will be equal to cos 24 pi t. Okay. So this is how the high pass filter will work. It will reject all the content which is less than cutoff, and it will pass only those content which has whose frequency is more than this cutoff frequency. Let me go to the next slide. Next is the band pass filter. So in this case, filter will pass a kind of band pass signal, and it will reject the low frequency signal and high frequency signal. Okay. So in this case, we have a two cutoff frequency. One is omega c1, one is omega c2. So from omega c1 to omega c2, whatever the signal is in this range, it will pass through the system. If the signal is out of this range, it will get blocked by the system. So now I have taken this filter. So now in this case, omega c1 is 5 pi, omega c2 is 10 pi. Okay, so any signal which has frequency from 5 pi to 10 pi will pass through this filter, otherwise it will get rejected. Okay, so the first signal which we have here is cos 6 pi t. So in this case, cos 6 pi t is within this range, so it will pass through the filter. It will be cos 6 pi t. Second one is outside the range, so it will become 0. Okay. In the third one, this is the DC, so it will get rejected because it is not passing any DC. And this cos 4 pi t will also get rejected because again this is somewhere here, and this cos 24 pi t, this will also get rejected, this is somewhere here. So in this case your yt will be equal to 0. Okay. So this is how the band pass filter works. Now, this Fourier transform we use to calculate the steady state signal. If some input signal is given, then what will be the steady state output? Okay. So, how do we calculate the steady state is, let's say we have been given uh, a cos omega naught t as an input, and we have been given some either h of t or h of omega, any one of them, and we need to find out if we apply this signal, what will be the steady state output. Okay, so the steady state output is given as, you just take the same signal a cos, okay, and modify its phase and its amplitude. Its frequency is not going to change, frequency will remain same, which is omega naught t here. Only the phase and the this amplitude is going to change. Now, what will be the modified amplitude? So, original amplitude was A. Now, this amplitude A will get multiplied by h of omega naught, okay, which is the value of h of omega at omega equal to omega naught. Okay. Now, this phase is the angle of this. So, we know that this h of omega is a complex number. So, it will have the magnitude part and it will have the phase part. Okay. So, this magnitude part we are taking in the amplitude term, and this phase part we are putting it in the phase term. Okay, so this is how we calculate the steady state of the system output. So let's say we have a signal which is equal to 4 cos 2t, which is the input of the system, and it is passed through a system whose impulse response is e to the power minus 2t ut, and we need to find out what will be the steady state response of the system. Okay. So in this case, this is the xt 4 cos 2t. Now, if you see this 2 is 2 is our omega naught. So omega naught is equal to 2. Now this is the ht. We need to first calculate the h of omega. So we know that from the Fourier transform of this signal will be 1 by j omega plus 2. Okay. So this is the h of omega. Now we need to find out what will be the mod of h of omega. So the mode of h of omega will be 1 by root omega square plus 2 square, and angle of h of omega will be given as minus tan inverse omega by 2. Okay, imaginary term divided by real term, and we are putting minus sign because it is in denominator. Okay, now here this is general form like h of omega and angle of h of omega. We need to find out this magnitude and angle term at omega equal to omega naught. Okay, which is 2 here. So mod of h of 2 will be equal to 1 by under root 2 square plus 2 square, which is equal to 1 by 2 root 2. And then we need to calculate the angle of h of 2, which will be equal to minus tan inverse 2 by 2, because omega is 2 here, which is equal to minus pi by 4. Okay, so we have got the angle term, we have got the amplitude term. So finally output, steady state output will be given as 4 cos 2t minus pi by 4, and it is getting, amplitude is getting modified by this h of omega. Okay, so finally you can write it as a root 2 cos 2t minus pi by 4. Okay, so this will be the system out, steady state system output if input is cos 4 cos 2t. Okay, so generally this kind of problem will be given when the input is either sinusoidal or combination of some sinusoidal or DC plus some sinusoidal or just a DC. Okay, so it will not be some arbitrary signal. It will be a signal which is something like some cos or sine or some DC or sine plus DC or cos plus DC and so on. Okay, so it will be in those kind of format.
Sir, one doubt, sir.
Yeah.
Sir, actually, how did this formula arrive? Like this h of omega naught exactly at that point, the steady state. What is the connection that formula with the steady state actually?
This one.
Yes, yes, that formula actually.
Okay, actually we derive it into the frequency domain and put it back into the time domain. So now let's say we have h of omega. I will just quickly show you. So it will be given as mod of h of omega and e to the power j of theta omega. Let's say this theta omega is angle and h of omega is magnitude. Now this is the x of t. X of t you can write it as a in x of omega is equal to, so this is the cos, right? So when you take its frequency domain, it will be two impulse. Okay? So this two impulse will be located at minus omega naught and plus omega naught. This is the Fourier transform of the cos. Okay,
Okay, okay,
so this is a by 2 and this is a by 2, so you can write it as a by 2 del omega plus omega naught and plus a by 2 del omega minus omega naught. Okay, now this x of omega will get multiplied by this h of omega to calculate y of omega. Okay, so y of omega will be given as h of omega e to the power j theta omega multiplied by a by 2 del omega plus omega naught. Okay, plus a by 2 del omega minus omega naught. Okay, now this is del which you are multiplying it to some function. So I will invoke this rule that when you have a del t minus a into x of t, you can write it as a x of a into del t minus a. Okay,
yes,
so here it is in time domain, here it is in frequency domain. It doesn't matter like whether it's a time domain signal or frequency domain signal. This rule is going to be applied everywhere. So you can write it as a h of omega naught. Okay. Uh, in this case, it will be minus omega naught. So h of minus omega naught e to the power j theta minus omega naught a by 2 del omega plus omega naught. Okay. And then for this term, you can write it as a by 2 del omega minus omega naught and h of omega naught e to the power j theta omega naught. Okay. Now after this, you can again combine them and bring it back to the, let me just rub this. Now if you see this complete thing, this is constant because now it's not omega, it's omega naught. This is also a constant because it is now omega naught, not omega. This is also a constant and this is also a constant. Only variable is this two. Okay,
okay,
now let's bring it back to the time domain. So when you bring it back to the time domain, it will become h of minus omega e to the power j theta minus omega a by 2 e to the power j minus j omega naught and plus a by 2 e to the power j omega naught h of minus omega naught, and actually this is mod here, right? This one is mod here. Okay, and then e to the power j theta omega naught. Now here we are talking about the real system. So what happens that we know that this magnitude spectrum is an even function of omega and phase spectrum is odd function of omega. So because of that, this term you can simply write it as a h of omega naught mod because this is even function of omega. This one you can write it as e to the power minus j theta omega naught because phase is odd function of omega, and then a by 2 e to the power minus j omega naught. Okay, plus a by 2. Okay, wait, yeah, this is plus actually here, and then e to the power j theta omega. Okay, Now, if you see this complete thing, you can take the h of omega naught a by 2 common. You will be left with e to the power j theta omega naught. Wait, there is something missing. Oh yeah, here e to the power j omega naught. Actually, when you take it in time domain, there will be t here. Yeah, there will be t. So e to the power j theta omega naught plus e to the power j, sorry. So here what now I'm going to do is I'm just going to combine this exponential power into the single term. So I can write it as a e to the power j theta omega naught plus j omega naught t, and then plus this two term e to the power minus j theta omega naught plus j omega naught t. Okay, so again it is back to our cos form. You can take this 2 here, okay, and there is a mod here. Okay, so now if you see this thing, when you take it back to the cos form, it will be same as what I have written here.
Okay, okay,
Correct. You
yes.
have magnitude modification h of omega naught, and then you have phase modification. So instead of omega naught t, you have omega naught t plus this phase term. Is it clear?
Okay. So it becomes a cos term with omega naught t and another exponential term with
That is
omega.
angle. Yeah.
Okay, okay. It's
This
written
is
as
what we call it as
angle.
angle of h of omega.
Okay, okay, okay. Uh, so my so so actually I have asked is that um, how the steady state that name here comes for this is the output. So how can this be the steady state? Like is it based
So,
on this
okay, let me tell you two things over here. Why we call it as a steady state. So let me go to the next slide then. Okay. So let's say if your signal is given as just simply cos omega naught t is the input. So output will always be written as h of omega naught mod cos omega naught t plus angle of h of omega naught. Okay, this is the case when input is simply cos of omega naught t and nothing is multiplied here. Now let me take a case where you have a cos of omega naught t into u of t. Okay, in this case, when you apply this as an input, uh, output will not be always given as by this formula. Okay, because when you apply this input to the system at the beginning, there will be some kind of response, like it's going up and down, like it will have some kind of rise time, some settling time, and so on. And after some time it will settle, and that we call, let's say, t tending to infinity. It is going to settle, and that we call it as a steady state. Okay, so here, because of this multiplication by ut, we don't have any cos, and that t equal to 0, we have got this cos signal now. Okay, so when you suddenly apply this cos signal at the output, immediately you will not get this cos signal. You will have some kind of transient response, like some kind of settling. I think this might be covered in the control system. So it will have some settling time, and at t tending to infinity, it will settle to finally this value. Okay, so for
okay,
this signal is always cos omega naught t from minus infinity to infinity. So if you take any time, let's say some finite time, let's say some negative time or positive time, but it has to be some finite time. With respect to this time, the signal is already applied at infinity time before, right? And
okay,
so if you take any time, it is kind of a steady state, because here it has started at t equal to minus infinity, but this signal is starting at t equal to 0. So for this, to check the steady state here t has to be tending to infinity. That's what we call it as a steady state. Okay, so for this kind of signal, there is like a steady state is like for every time you can plot on the this axis. Okay, but for this kind of signal, the steady state occur only at t tending to infinity.
Okay.
Is it clear?
Clear.
Okay. So let me attempt one question. So this is the one of the problem asked in the gate EC. So this is based on this problem that just now we solved. So we have been given a linear time invariant system filter where the impulse response is given by this. Okay. So this is the impulse response. So when you plot this is impulse response, it is how it is going to look like. Okay. Ht equal to 3 from t equal to 0 to 3. Now, in this system, we are applying an input of value 5. This is just a constant input of 5. We need to find out what will be the steady state output. Okay. Now, here we are talking about the constant input 5. So when you plot into the time domain, it is always going to be 5. This is a constant. Now, when you take into the frequency domain, you'll get just a DC signal 5 into delta of omega. Okay. So if you take this signal and calculate its frequency content, it is just going to be DC signal. It means that here omega is equal to 0 in this case. Okay. Now, since omega is equal to 0, now in this case, when you calculate the output yt, it will be equal to input number that we have here multiplied by what is the amplitude of the signal at this, and there won't be any phase here because it is DC, and DC at DC frequency LTI system generally doesn't contribute any phase. Okay, so there won't be any phase lag here. There will be only amplitude modification, and this term we need to find out what will be the mod of h of omega naught. Okay, and here omega naught will be equal to 0, so I can simply write it as h of 0 multiplied by 5. This is the number we need to find out. Now, here you don't need to calculate the Fourier transform to find out the h of omega naught, because we know that h of omega is equal to h of t e to the power minus j omega t dt minus infinity to infinity. Okay, so h of 0 can simply be written as minus infinity to infinity h of t dt. Okay, you don't need to calculate h of omega and then put omega equal to 0. Just put omega equal to 0 directly here, and then it will be simply the integration of ht, or you can say area under the ht, area under the curve. And in this case, it is equal to 9. Height is 3, width is also 3. So this will be equal to 9. So you can write it as a 9 into 5, which is 45. Okay. So in this case, the output, steady state output will be equal to 45. Okay. So here we didn't apply any kind of phase lag because omega is equal to 0, and we just need to find out what is the amplitude at omega equal to 0. Now, if instead of this DC, if you are given some, let's say some cost, some number, in that case, you need to find out what will be the phase and what will be the uh, magnitude. Okay, this amplitude here. In that case, you need to find out both. In this case, you don't need to find out the phase, and in that case you need to calculate the h of omega. Okay, here we got away with this because we need to just calculate h of 0, and which is pretty easy by this formula. But if it were some other omega, let's say some omega not equal to 2 or something, then in that case you need to find out the h of omega and then proceed with that. Anyone has any doubt here?
Clear.
Okay. Yeah. So let me just briefly talk about the last topic of the Fourier transform. So this is called the distortionless system. So any system is called as a distortionless system when you give the input and output will be simply the either delayed version of the input and some modification in the amplitude or attenuation in the amplitude. So for example, let's say I'm sending the triangular signal. Output should also be a triangular signal. It may have some amplitude modification, it may have some delay, time delay. Let's say this is 0, this is 2, so this will be, let's say, 4 and 6, and this, let's say this is 1, so this can be 2. So there can be some amplitude modification, there can be some delay, but it should not change the property of the signal. So what I mean by property is that if you are sending the triangular, it should not make it some kind of rectangular or some kind of other signal. Okay, so if you are giving the sine, output should also be sinusoidal signal. If you are giving the rectangular, output should also be rectangular. The system should do only the amplitude modification and the delay, time delay mode. Okay, so it means that you can write the output as a amplitude modification of the input and some delay. Okay, so this should be the relationship between the input and output of the distortionless system. It is just introducing some amplitude modification and just introducing some delay here. Okay, so this is the input output relationship of the any distortionless system. Now let's take the Fourier transform on the both side. So by applying the property, this will be the Fourier transform, and from there you will get the this h of omega, which is the transfer function of the system, and it will be given as this a e to the power j omega t naught. Okay, now if you take the magnitude of this, it will be always be a constant, and when you take the phase of this, it will be omega into t naught. So when you plot the magnitude spectrum of the system transfer function, it will be a constant a. Okay, and when you plot the angle of the h of omega, it will be the linear function of the omega. It will be changing linearly like this. Okay, so any system whose transfer function has this kind of magnitude spectrum and this kind of phase spectrum, such system is called as a distortionless system. So amplitude spectrum should be constant and the phase spectrum should be linear function of omega. That kind of system will be a distortionless system. Okay, by this with this the Fourier transform is over. I will start a new topic, that is the discrete time Fourier series, and then we'll go to the discrete time Fourier transform. So it happened. Okay. So just like we have a period this continuous time Fourier series for the continuous time periodic signal, we have discrete time Fourier series for the discrete time periodic signal. Okay. So we have a, let's say, signal x of n, which is a periodic signal, which means that it is going to repeat itself by every n. So for this particular signal, we can calculate what will be the Fourier series, just like we have calculated it for the continuous time. So the Fourier series is given as x of k equal to 1 by n and summation over n and x of n e to the power minus j k omega naught n, where omega naught is equal to 2 pi by capital N, okay, where capital N is the time period. Okay. Now here in this case, let's say we want to calculate what will be the x of omega. Okay, this x of sorry, x of 0 here, capital X of 0. So it will be putting you will be putting k equal to 0 here. So this exponential term will go away, and you will be just adding the x of n. Okay, so this x of 0 can be written like this. Okay, now if you try to calculate the x of n here, okay, x of capital N, that turns out to be same as x of 0. Okay, so which means that the Fourier series coefficient of this discrete time signal will also be a periodic. Okay, so here that in the time domain we have a periodic signal. In the Fourier domain also, the Fourier coefficient will also be a periodic. Okay, so x of k will be given as x of k plus capital N. Okay, this property is not there for the continuous time. Okay, continuous time signal will be periodic in the time domain, but when you take its Fourier series c of k is never equal to c of k plus t naught or something like that. Okay, so in this case, this is the only for the discrete time that we see this property that if you have a discrete time signal, its a Fourier coefficient will be periodic. Uh, just remember that this for this continuous time signal, this will not be a periodic. Only for the discrete time signal, we see this. We see that this is a periodic. Now let's take an example. Quick example. Let's say we want to find out what will be the Fourier series of this signal 2132. So this is a periodic with n equal to 4. What it means is that it will be like 2132, and then it will repeat itself 2132, 2132, and it will continue on the right side as well as on the left side. Now let's say we want to find out what will be the Fourier series for this case. Yeah. So we will use that formula, that summation of x of n e to the power minus j k omega naught and 1 by capital N. So capital N is 4, so 1 by 4. Now for x of 0, it will be simply the summation of all this term divided by 4, which will give me 2. Okay, because for x of 0, you will be making this k equal to 0, and this complete thing will become 1. Okay. Now for x of 1, it will be given as 1 by 4. First term will be simply 2 coming here. Second term 1 will come here, and then there will be exponential to the power minus j, and k is 1 here 1, and omega naught will be 2 pi by 4, and n is 1. Okay, so that's why it is e to the power minus j 2 pi by 4. Second term is 3, so this 3 is here, e to the power minus j 4 pi by 4, and this 2 is here, and then e to the power minus 6 by j by 4. Okay, so when you solve this thing, you'll get 1 by 4 minus 1 plus j. Similarly, when you calculate it for x of 2, you will get 1 by 2, and when you calculate it for x of 3, you'll get 1 by 4 minus 1 minus j. Okay. Now if you see this this x of k calculation, you will see that this x of 1 and x of 3 are complex conjugate. Okay, here you see these two are complex conjugate number. So there is a special property for the discrete time Fourier series, and that is that let's say you have a signal I am now giving a different example to explain this property. So let's say we have a signal with period n 8. Okay, this period n is equal to 8. So since this time the period is 8, we will be calculating the signal from x of 0 to x of 7. Okay, in this case period is 4, so that's why we calculated only this value, x of 0 to x of 3, and then x of 4 will be same as x of 0 because it is periodic, so we generally don't calculate those things. So x of 0 and x of 2, x of 7 we need to calculate. Okay, so x of 0 we know that we need to just add all the x of n and that divided by time period. That is pretty easy. Now this x of 1 will be complex conjugate of the x of 7. Okay, this x of 2 will be complex conjugate of x of 6, and x of 3 will be complex conjugate of x of 5. Okay, this is the property for the discrete time Fourier series. Okay, so if you calculate just the x of 1, no need to calculate x of 7, you can just take the complex conjugate and find the x of 7. Similarly for x of 2 and x of 6, and x of 3 and x of 5 also. Okay, so like that you can calculate the uh, Fourier series just by applying the complex conjugate. So just calculate the x of 3, do the complex conjugate, and you'll get x of 5. Anyone has any doubt here? Okay, so this is the case when you have a time period which is equal to an even number. Let me take a case when the time period is an odd number. So let me take the case of 7, n is equal to 7. So in that case, we will be calculating it from x of 0 to x of 6. Okay. Now in this case, let's say we have x of 1, x of 2, x of 3, and x of 4 and x of 5. Okay. Again, in this case, x of 0 will be given as summation of all of x of n divided by 7. Okay. Now, in this case, this x of 1 will have complex conjugate x of 6, x of 2 will have x of 5, and x of 3 will have x of 4. Okay. Now, in the first case, when we have period equal to 8, you see in the middle you are leaving one term, x of 4. In this case, you don't have any term here in the middle. Okay. So in this case, like you don't have any term in the middle, so you for except x of 0, for the rest of them you have complex conjugate term. So for x of 1, x of 6, x of 2, x of 5, and for x of 3 you have x of 4. Here in this first case you don't have any complex conjugate for x of 4. So that will be the difference when you go from odd to even or even to odd. Let me go to the next slide. So this is the problem given. One of the I've taken it from one of the gate problem. So a discrete time periodic signal is given, and here AK is the Fourier coefficient of the signal, and the coefficient AK are non-zero, where K is equal to Bm plus 1, where M is any integer. We need to find out the value of B. Okay. Now here we need to find out what is the Fourier series coefficient, and for which all value of the k, the coefficient is non-zero. Okay. Now remember from the continuous time Fourier series that whenever we have been given a sinusoidal signal like cos or sine, instead of directly calculating the Fourier series, what we do is that we write this sinusoidal signal in terms of exponential, and then we will compare it with our Fourier series formula to find out the coefficient. Okay. So the same thing we will do here. So if you this is the equation that we are going to use to compare it, that x of n is equal to summation of x of k e to the power j k omega naught n. So let me write it here. X of n is equal to summation of, in this case it is written as a of k, so I will write it as a of k instead of x of capital K e to the power j k omega naught n. Okay. Now this x of n, you can write it as a so this is sine. I will write it as e to the power j pi n by 5 minus e to the power minus j pi n by 5 by 2j. So this is the x of n. Now this x of n in this Fourier series expansion, I can write it as a of k e to the power j k. Now we need to find out what is the omega naught here. Okay. So this omega is here as a pi by 5. We know that how to find out the time period, so divide it by 2 pi, so it will become pi by 5 by 2 pi. This pi and pi will cancel out each other, and this will become 1 by 10, and this capital N we call it as a, so this 10 we call it as a capital N, right? This is the time period. Okay, so this is the time period, so omega naught will be given as 2 pi by capital N, and which is equal to 2 pi by 10, which is equal to pi by 5. Okay, here it looks like we can directly put it here, but in some case what happens that this is not very straightforward that we just directly put it here to find out the omega naught. In some cases you need to take this ratio, find out what is the capital N, and then do the omega naught equal to 2 pi by capital N. Okay, sometimes this number will not be same as this number. So now we have got omega naught equal to pi by 5, so I can write it as summation over a of k. Okay, I can directly write it here. K omega naught is pi by 5. And now if I compare this with this, you will see that we have pi n by 5. Here we have pi n by 5. And this you will get only when you put k equal to 1. And similarly for k equal to minus 1, you will get this. Okay. So it means that for k equal to 1 and k equal to minus 1, you will get ak, which is equal to non-zero value. Okay, so you can write, so k is equal to bm plus minus 1, and this is equal to plus 1 and minus 1, which means that b is equal to 0. Okay, anyone has any doubt in this? Okay, let me go to the next slide then. Let's just quickly go through the property of the DETFS. So again, linearity property. So this is like universal we have been seeing. If you have a ax of n, by of n, and both are periodic, so the resultant will be ax of k and by of k. Second thing, I already discussed that x of k is a periodic say. Okay, so whatever the time period we have, the same period we have for the x of k also. Next is the conjugate symmetry. So again, it is same as what you have seen in the Fourier transform. So let's say you have x of n, which is a real signal. In that case, x of k conjugate will be given as x of minus k. Now, this x of minus k, you can write it as x of n minus k, because this x of k is a periodic. So whether you add this n here or not, it doesn't matter. Okay. Now, here we know from the Fourier transform derivation that whenever the xn is real, or in the Fourier transform it was x of t, its Fourier transform x of omega will have the magnitude term and the phase term. Magnitude will be even function of omega and phase term will be odd function of omega. Same thing is here, that magnitude of the x of k will be even function of k, and x of k, phase of the x of k will be odd function of k. And again, if same as Fourier transform, if signal is real plus even, x of k will be real, and signal is real plus odd, x of k will be imaginary. So again, when you have a x of n which is composed of odd plus even signal, odd signal is responsible for the imaginary part, and even signal is responsible for the real part. We go to the next slide. Next is the convolution in the time domain. Okay, so here we know that the signal is periodic in the time domain. So there is a special convolution that we call it as a periodic convolution. So whatever the convolution that till now we have seen is what we call it as a linear convolution. Okay, so in the linear convolution, it is given as x of k, h of n minus k, and k is varying from minus infinity to infinity. Okay, in the case of periodic convolution, the formula changes, that it will vary from k equal to 0 to capital N minus 1, x of k, h of n minus k. Okay, so in this case, we have a signal x and h, both are periodic with the same time period, which is capital N. And then you can apply this this is a circular convolution. So the different, you can see the difference here. It is k is varying from minus infinity to infinity. Here the k is varying from 0 to n minus 1. So that is the difference between the circular convolution and the linear convolution. Linear convolution is applied when the signal is aperiodic. Circular convolution is applied when the signal is periodic signal. Okay. Now here in the time domain, if it is convolution, on the frequency domain it will be multiplication. Okay, it is very universal property, where in the convolution, if it is a time domain it is convolution, then in the k domain, on the frequency domain, it will be multiplication. Now multiplication in time domain will be convolution in the k domain. Now again, the k domain is also a periodic, right? We know that when you take the calculate the x of k for x of n and z of k for z of n, this x of k and z of k will also be periodic. And because of that, instead of doing the linear convolution, in the right side we will do the circular convolution. So this is the circular convolution of the x of k and z of k. Okay, next is the time shifting. So again, it is very similar to what we have seen in the Fourier transform. You just multiplied by e to the power j k omega naught n naught on the frequency k domain. In the frequency domain, you will be multiplying it with e to the power j k omega naught n. Next is the Parseval's theorem. So according to this theorem, the power in the time domain will be same as the power in the k domain. So this is the power we calculate for the periodic signal. Okay. If you remember from the beginning of the class, so this is the power of the periodic signal, and this is the power of the periodic signal in the k domain, and this two will be same according to the Parseval theorem. Let me go to the next slide. Yeah. So that is all about the DTFS, discrete time Fourier series. I will start a new topic that is a discrete time Fourier transform. I will take a 5-minute break and then uh, I will again start the class here. So we'll jump to the new topic that is the discrete time Fourier transform. Now, if you remember, so you can again correlate this with the uh, uh, our continuous time Fourier transform. So the discrete time Fourier series we calculate only for the periodic signal, but discrete time Fourier transform you can calculate it for the periodic as well as aperiodic signal, just like the continuous time Fourier transform. Okay. Now, if you remember the Z transform was given as h of z is equal to summation n is equal to minus infinity to infinity x of n z to the power minus n. Okay. Now in the Z transform, if you replace this, Z is equal to e to the power j omega, you'll get the discrete time Fourier transform. Okay. So the discrete time Fourier transform will be given as for any signal x of n. This is the formula. So n equal to minus infinity to infinity x of n e to the power minus j omega n. Okay. And if you can calculate the inverse Fourier transform also, so that will be given in by this formula. 1 by 2 pi minus pi to pi x of e to the power j omega, e to the power j omega and d omega. Now again, this x of e to the power j omega is a complex number, so it will have the magnitude term and the phase term. So this can be written as a magnitude term and the phase term. Okay, and just like the we have the criteria for the DTFT to converge. So the DTFT will converge if it satisfies this property. Okay. So if any signal will satisfy this property, then its DTFT is going to converge. But that doesn't mean that if it is not satisfying this property, it will not converge. If it is not satisfying this property, it may or may not converge. Okay. So if it is satisfying this property, then DTFT exists. Okay. And if it is not satisfying this property, then it may or may not exist. Okay. So when this is not true, generally people make just opposite assumption that there is no existence of DTFT, but that is not true. If this is the case, then it may or may not be there. Okay.
Example.
Okay. So here generally we don't calculate the DTFT directly, because when you try to calculate DTFT directly and any signal is not satisfying this criteria, then it will result to the infinity. But there is some indirect method. For example, I will show you guys one example. So let's say we have some signal which is integration of some other signal. So I can use the integration property to calculate the DTFT. Okay. So the first property of the DTFT is the periodicity. So in the time domain it is aperiodic, but in the frequency domain it will be periodic, and the periodicity is 2 pi here. But in the case of continuous time, this was not the case. In the continuous time, it was aperiodic. Next is the linearity. So linearity is pretty easy. Like you just need to, whatever the scaling you're doing here, you need to do in the frequency domain also. This is a time shifting. You will just multiply with e to the power minus j omega n naught in the frequency domain. And when you do the frequency domain shifting in the time domain, you will be multiplying it with e to the power minus j omega naught n. Again, since this x of e to the power j omega is a complex number, this can be written in the magnitude and the phase term. And if x of n is a real, then its magnitude spectrum will be even function of omega, and its phase spectrum will be odd function of omega. So till now, whatever the Fourier transform we have seen, whether it's a Fourier series, continuous time Fourier series, or discrete time Fourier series, or continuous time Fourier transform, or discrete time Fourier transform, for all four of them, this property is universally true, that when the signal is real, its magnitude spectrum will be even function, and its phase spectrum will be the odd function. Okay? And if it is a real plus even, then its frequency domain, it will always be real. And if it is real plus odd, in the frequency domain, it will be in imaginary. So in general, if you have a signal which is composed of real plus odd, then the odd is correspond to this imaginary term, and the even correspond to this real term. Now here, let's say, so this is the problem I've taken from the ISRO. So Fourier transform of the discrete time aperiodic signal is, okay. So in the time domain, it is discrete and aperiodic, okay. But in the frequency domain, we write it as a x of e to the power j omega, and this is continuous, okay. So this is continuous function, and we know that this is periodic with period 2 pi. Okay, so x of e to the power j omega plus 2 pi is same as x of e to the power j omega. Okay. So now let me quickly summarize one like observation here. So if you have a continuous time periodic signal, so this is the time domain I'm talking about, and then on the right side I'm talking about the frequency domain. Okay. So if you have a continuous time periodic signal, in the frequency domain we get the discrete frequency, right? Because for the periodic signal we calculated the Fourier series Ck, which was discrete in nature. So it will be discrete in frequency domain, and it will be aperiodic. Okay. Next was the continuous time aperiodic. So for this one we got continuous frequency. Okay. In the frequency domain it was continuous, and again it was aperiodic. Okay. Now we just discussed about the discrete time. So let me write that discrete time periodic. So discrete time periodic is also discrete and periodic. And discrete time aperiodic is continuous and periodic. Okay. Now you see that whenever the signal is continuous time in the time domain, whenever the signal is continuous time, the common property on the right side is aperiodic. Okay. So whenever the signal is continuous time domain signal will be aperiodic always. Okay. Now whenever the signal is discrete time on the frequency domain, it will be periodic. So discrete time, it will be periodic. Now whenever the signal is periodic, whether it's a discrete time or continuous time, it doesn't matter. Whenever the signal is periodic, frequency domain, the common factor is discrete. Okay. Whenever the signal is periodic in the frequency domain, this is discrete. So for periodic signal, frequency domain will always be discrete, and for aperiodic signal, frequency domain will be continuous. So based on what combination you have, whether you have continuous time periodic signal, for that you'll get periodic and discrete signal. For continuous time aperiodic signal, you'll get aperiodic, continuous signal, and so on. Okay, so that's how the property looks like for when you go from the time domain to the frequency domain. So continuous or discrete time is related to the periodicity, and periodicity is related to the discrete and continuous. Anyone has any doubt here? Let me go to the next slide then. Okay. So in this problem, we need to find out what is the DTFT of this signal. Okay. So this signal is given, and we can apply simply this formula that x of e to the power j omega, which is equal to summation of x of n e to the power minus j omega n, and equal to minus infinity to infinity. Okay. Now in this case, this is n equal to 0, this is n equal to 1, this is n equal to 2, this is n equal to minus 1, this is n equal to minus 2. So we have signal only from n equal to minus 2 to 2 x of n e to the power minus j omega n. For rest of the n, it's 0. So let me put the values here. So for n equal to minus 2, value is minus 2. It will become e to the power minus j. Wait. E to the power j 2 omega. Then minus 1 e to the power j omega. Then plus 0 plus 1 into e to the power minus j omega plus 2 into e to the power minus j 2 omega. Okay. So this is the Fourier transform we got, but now you can combine this 2, and this 2 with this one and get the either sine or cos form. So let's see what we are getting here. So when you take the minus 2 common here, you'll get e to the power j2 omega minus e to the power minus j2 omega. And for this one, you'll get, when you take the minus 1 common, e to the power j omega minus e to the power minus j omega. Okay. Now divide it by 2j, multiplied by 2j, and similarly here also divided by 2j and multiplied by 2j. Okay. So this will become minus 4j sine 2 omega, and this will become minus 2j sine of omega. When you take the minus 2j common, you will get 2 sine 2 omega plus sine of omega. Okay. So this will be the correct answer. So this question are pretty straightforward. You need to just simply apply this discrete time Fourier series formula. Now next property is the difference property. This difference property is pretty straightforward. X of n is same as x of omega, and x of n minus 1 I'm just use the time shifting property. So this is the difference. Now this difference is kind of differentiation in the time domain. Okay, it is kind of equivalent to that. Now there is an accumulation which is like kind of summation here. This accumulation is kind of integration in the time domain. Okay, so this differentiation and integration are kind of opposite of each other. Similarly, this difference and accumulation are kind of opposite of each other. So in the difference, if you are multiplying it with 1 minus e to the power j omega, in the accumulation, you will be multiplying it with, there is omega term here, 1 by e to the power minus j omega x of e to the power j omega. Okay. Other than that, we will get some term which we call it as a DC term, and this term we are getting because once you do the difference, some of the DC term will go away, but when you do the accumulation, it will come back. So to represent that, there is a DC term here. Next is the time reversal. So when you do the time reversal, it will simply be the frequency reversal here. Differentiation in the frequency domain, it will result in the multiplication by n here. And here, since we are talking about the mostly the aperiodic signal, so the energy in the time domain will be same as the energy in the frequency domain. Now here we are talking about the signal which are aperiodic. So here when you do the convolution, this is linear convolution. Okay. And in the frequency domain, it will be multiplication. Now, when you do the multiplication in the time domain, in the frequency domain, it will be convolution, but these two signal are periodic signal. Okay. Since these two signal are periodic signal, this convolution will be circular, not linear. Okay. Because this x of e to the power j omega and z of e to the power j omega both are periodic with 2 pi. Okay. Now, yeah, so this is the so as I told at the beginning, right? So let's say you have a signal which is not satisfying this criteria, that summation of x of n less than infinity. If it is not satisfying this criteria, then it may or may not have the this discrete time Fourier transform. Okay, so I will show you one example. Let's say we are talking about the unit step. Okay, so the unit step is equal to 1 from n equal to 1 to infinity. Okay, so it is equal to 1 if you plot it with respect to n from n equal to 0, 1, 2, 3 till infinity. If you put this into this one, summation of u of n equal to minus infinity to infinity, this will result in infinity because you have all the time ones and you are adding them infinite time. So this will give us infinity. So this is not satisfying this criteria, but still we will be able to calculate the DTFT of this. So we can use the property of the accumulation. Okay. So before that, we will calculate what will be the DTFT of the del of n. So del of n just exists at n equal to 0 for rest of the time. It is equal to 0. So only for n equal to 0, it is equal to 1. So when you calculate the x of e to the power j omega for this one, minus j omega n. So since signal is there only for n equal to 0, when you put n equal to 0, you'll get simply delta n. Okay, or you can say, no, not delta n actually, simply 1. So you'll get 1 here. Okay. So this is the DTFT of the impulse. Now, unit step is given as the accumulations. Okay, if you remember from the first class, so unit step will be given as accumulation of the impulse. So we can apply the accumulation property to find out what will be the Fourier transform of this one. So what was the property? So the property was that m equal to minus infinity to n x of m. The Fourier transform for this one will be x of e to the power j omega divided by 1 minus e to the power j omega plus pi into x of e to the power j0. Okay. So this is the property that we are going to use. So x of e to the power j omega, where x is impulse. Okay, we are doing the accumulation of the impulse. So which is equal to 1 here. So 1 by, so there is a minus sign here. 1 minus e to the power minus j omega plus pi x of e to the power j0. And x of e to the power j0 will be equal to 1. Okay. Oh, wait. Oh, del omega. So this one finally, when you calculate this, this will, so this is the final answer. Okay. So when you calculate this, this term is as it is here. And when you see this term, you have pi del omega x of e to the power j0, and x of e to the power j0 is equal to 1. Okay. Because the Fourier transform of so which is equal to 1, and it is equal to x of e to the power j omega. So when you put omega equal to 0 also, it is equal to 1. Okay. So this will be equal to 1. So since this is equal to 1, you'll get pi into del of omega. So you see that for this case, which is not satisfying this criteria, but still we are able to calculate its Fourier transform with the help of some property. Okay. So in this kind of cases where it is not satisfying this criteria, the direct calculation will not exist, but indirectly with the help of some kind of property, you might be able to calculate. Okay. I'll just quickly go through few DTFT. So let's say we have a signal which is a to the power n un, where a is less than 1, and we want to calculate what will be the DTFT of this signal. Okay. So the DTFT of this signal, I can write it as n equal to 0 to infinity. I'm writing it from n equal to 0 to infinity because u of n is already there, and because of that the signal will become start from n equal to 0. Then a to the power n e to the power minus j omega n. So you can write it as a, so if you expand it, you'll get 1 plus a e to the power minus j omega plus a square e to the power minus 2 j omega, and so on. Okay, and this is GP, and this GP, so here first term is 1 and r is equal to a into e to the power minus j omega. So you can write it as a 1 by 1 minus r, which is equal to a into e to the power minus j omega. Now here I have written this GP equal to this one because here in this case r is less than 1, or I can say mod of r is less than 1, because here it is written that a is less than 1. Okay, but in the case when a is greater than 1, you will not be able to calculate the DTFT of that signal, and in that case the DTFT doesn't exist. Okay, so if you have a signal e to the power n un and a is greater than 1, in that case DTFT doesn't exist. So even with, if you try to find out with some property, with that also you will not be able to find out the DTFT of this signal. Okay, so the DTFT of this signal doesn't exist. This one we have already calculated. This one is equal to 1. These two question you guys can try to solve at home. This is again pretty easy. You can simply calculate it. So when you calculate this problem, you'll get some kind of sinusoidals in the frequency domain. Go to the next slide. Now this is interesting problem. Here we need to use some kind of property to find out the DTFT of the signal. Okay. So here the signal is given as n plus 1 alpha to the power n. Okay. I think there is a un here. U is missing. And alpha is less than 1. For this signal, we need to find out what will be the DTFT. Okay. So you can write the yn is equal to n into alpha to the power n un plus alpha to the power n un. You can divide this signal into two parts. This one we already know what is the DTFT. For the second one, you need to apply some property to find out what will be the DTFT. So here in the time domain, we are multiplying it with n. So in the frequency domain, we will be doing the division by omega. Okay. So here we are using this property. So it is a multiplication by where is it go? Yeah, this one. Differentiation in the frequency domain and multiplication by n in the time domain. So we'll be using this property to solve this first term. So the second term is already clear. So this will be equal to 1 by 1 minus alpha into e to the power minus j omega. Okay. Now the second term uh, is clear. Now the first term has alpha into u to the power n. So alpha into, sorry, alpha to the power n un. For this one, the DTFT is 1 minus alpha e to the power minus j omega. Now when you multiply it with n, it will be equal to j d by d of omega 1 by 1 minus alpha e to the power minus j omega. Okay. So now this we need to calculate. So once you do the calculation, okay, so once you do the calculation and add this to here, you will get the answer. So let me just quickly calculate. So it will be j 1 minus alpha e to the power minus j omega square. There will be minus 1. Then there will be minus alpha e to the power minus j omega. Okay. So the final differentiation will look like this. Okay. Now we need to add this term with this term to get the answer. So now we will be adding this e to the power minus j omega. So this you can write it as a wait. There is a sign change. E to the power minus j omega. Right. Mm, okay, I'll put it here. So everyone is getting the same answer, right? This one. We continue. Okay. Now we will talk about the system, discrete time system. So again, we know that it will be output will be given as a convolution of the input and the impulse response. So in the frequency domain, it will become multiplication. Now let me, so here the sometime question can be given that like some impulse response or maybe input output relationship will be given, and you will be asked to find out what kind of system is it, whether it's a low pass, high pass, band pass kind of system. So let us take example that we have been given a system within this kind of input output relationship, and we need to find out what kind of filter is it. Okay. Now to find out what kind of filter is it, whether it's a low pass, high pass or band reject, we need to find out what is the h of e to the power j omega. Okay. And after finding the h of e to the power j omega, we will plot the magnitude and see how does it looks like. Okay. So to find out h of e to the power j omega, we will take the Fourier DTFT on both sides. And after taking the DTFT, you can calculate the y of omega divided by x of e to the power j omega. And you will get 1 by 2, 1 plus e to the power minus j omega. Okay, there is omega here. Now this one, you can write it like this. So just take the e to the power minus j omega by 2 common, and then you'll get this. And here you can take this 2 here and write it into the form of cos. Again, there is omega missing. So finally, this will be the h of e to the power j omega. Okay, so we need to find out what is the magnitude. So once you take the magnitude, you can remove this term and you'll just get cos omega by 2. Okay, so magnitude of h of e to the power j omega is cos omega by 2. Okay, now in this case, we know that h of e to the power j omega is periodic. Okay, and its period is 2 pi. So we will just going to plot this cos of omega by 2 only from minus pi to pi. Okay, which is the range of time period. Okay, Now we know that at omega equal to 0, this cos will be equal to 1. So this will be equal to 1. Okay. And then as you increase the omega, this is going to go down. Okay. Something like this. And at omega equal to pi, this will become cos pi by 2. And we know that cos pi by 2 is equal to 0. So at pi, it will become 0. And this is how it on the right side also. Okay. So if you see this filter, this is how the mod of h of e to the power j omega is going to look like. Okay. And if you see this, this is the pi minus pi and pi, which is the max frequency we just consider. Okay. We generally, when we talk about the discrete time, we don't go beyond pi and don't go beyond minus pi. This is what the range we consider, only from minus pi to pi. Now, if you see this kind of filter is passing the low frequency and kind of attenuating the high frequency. Okay, at the high, as you go from low frequency to high frequency, the amplitude is going down. Okay, so this filter, you can say that this is a low pass filter. This is not an ideal filter. Ideal filter looks something different. This is a kind of filter. You can say a practical filter. And this is a low pass filter because it is passing the low frequency and rejecting the high frequency signal. Okay. So sometime question can be asked like this. Input output relationship will be given. You need to find out what kind of filter is it. So you have to take that, calculate the h of e to the power j omega, and then see how does it looks like in the frequency domain when you plot it. Okay. So whether it's low pass or high pass.
Sir, can you tell me how to take previous one? Yeah.
How to take?
Can you repeat that thing, sir?
Okay. Okay. Let me just go through the filter, then it will be clear. Then yeah, I have the filter. Yeah. So this is the low pass filter. This is the band pass filter, and this is the high pass filter. Okay. So as I told, when we talk about the discrete times thing, we just care about the minus pi to plus pi. Okay. You can think of this minus pi as a similar to minus infinity of the continuous time, and this plus pi as a infinity of the continuous time. Okay. We don't care about the below minus pi and above minus pi because this thing is going to repeat itself. Okay. So when we talk about the low pass filter, so low pass filter is, this is how it is going to look like. So from it will also have a cutoff frequency omega c, and from 0 to omega c it is going to pass, and from omega c to infinity, it is not infinity, here it is pi. So omega c to pi it is going to reject. For the high pass case, from 0 to omega c it is going to reject, and from omega c to pi it is going to pass. Okay. So we just consider this till this pi. For band pass filter, from minus pi to this cutoff frequency, it will going to reject, and then from this point to this point it is going to pass, and again from this point to this point it is going to reject. Okay. So low pass, here the low pass, band pass and high pass looks similar to the what we have seen in the continuous time. Only the difference is that in the continuous time, frequency was varying from minus infinity to infinity. In the discrete time, frequency will vary from only minus pi to plus pi. Okay. So now let's come back to the filter that we just plotted few slides back. So it was looking something like this. Okay. And it was going up, then again going down. Okay. Now if you see this filter and compare it with this low pass, band pass, and this high pass, this it is a low pass filter which is very close to this filter, right? And that's why we call it as a low pass filter. Okay. This filter that I have drawn here, this is ideal filter. Ideally we want low pass filter to be like this, but generally low pass filter will not be, this kind of filter will not be realizable, so we use some kind of approximate filter. So this is the one of the example. Now is it clear?
Sir, yes, sir. But from the question, they said, we go. Can you go back to question?
Yeah.
Yeah, they have given from the question to how we convert that thing.
How we convert that thing? You mean how did we get h of this h of omega?
Yeah.
Okay, so this difference equation will be given in the problem. After that, we will take the Fourier transform on both left and right side.
Yeah.
DTFT. So when
Yes.
you take the DTFT of y of n, you'll get y of e to the power j omega. This you'll get x of e to the power j omega. And here
Yes.
use the time shifting property.
Yeah.
Okay. Now here you have x of e to the power j omega common. Just take it out. Here you will be left with this. Now h of e to the power j omega is equal to y of e to the power j omega divided by x of e to the power j omega. So just take this in the denominator here. So on the right side, you'll be left with 1 by 2 and this term.
Yeah.
Okay. Now is it clear?
Yeah. Yes, sir.
Okay.
And omega by 2, omega by 2.
Okay. This term.
Yeah.
Okay. So when you take the magnitude, right? When you take the mod of it, this term goes away, right? This is so for example, let's say you have 1 plus 2j. Okay. When you write in take the magnitude and the phase term.
One,
Okay. So this will be the magnitude 1 square plus 2
two,
square, and
one.
there will be some phase term. Phase term, when you take the magnitude of it, it becomes 1. This is exactly the phase term here.
Okay.
It will become 1.
Okay. Okay, sir.
Yeah. Now, a two discrete time system with impulse response this and this are connected in the cascade. The overall response of the cascade system is okay. So this problem, you can use this property that del n minus a convolution with x of, let's say, n minus b will be equal to not del, x of n minus a minus b. Okay. So here you can write del of n minus 1, and instead of writing this del of n minus 2, let me just write h2n here as of now. Okay. So this will become h2 n minus 1. Okay, by applying this property. Here the b is not there, that's why b is not here, only a is here. Now h2n is delta n minus 2, so h2n minus 1 will become delta n minus 3. Okay, so this will be the correct answer. Now this problem you can solve in the frequency domain also. So here you have h1n and it's del n minus 1. So h1 of omega or e to the power j omega will become e to the power minus j omega, and h2 of e to the power j omega will become e to the power minus 2 j omega. Now these two systems are in cascade, so their effective impulse response is the convolution in the time domain. So in the frequency domain, it will become multiplication. So h of e to the power j omega will become h1 multiplied by h2. Okay. When you multiply this 2, you'll get e to the power minus 3 j omega. Okay. And when you take the inverse Fourier transform, you'll get delta n minus 3. So this is the Fourier transform of delta n minus 1. Go to the next slide. Okay. The impulse response of the discrete time system is given as h of n equal to 0.5 delta n minus 2. The magnitude of the response can be represented as. Okay, so here we need to find out what will be the magnitude of the response. So h of n is given. So h of e to the power j omega, and here omega is written in some kind of ohm form. So I will write it like this only. Now 0.5 for delta n, Fourier transform will be 1. For delta n minus 2, Fourier transform will be e to the power minus 2 j omega. Okay. Now whenever you see this kind of thing, right, 1 plus something, take the thing common such that, so here I am going to take e to the power minus j omega common. So what happens that once you take the e to the power minus j omega common, this one will become e to the power plus j omega, and this one will become e to the power minus j omega. Okay? And then
Yeah.
you can divide it by 2 and multiply it by 2, and then this complete thing will become cos. Okay? This 2 into 0.5 will become 1, and this will become cos. So you can write e power minus j omega
Cos omega.
cos omega. Okay. Now this term again is a phase term. So when you go to and take the magnitude, this phase term will go away. Okay. This magnitude will become 1. You'll be just left with cos of omega. So mod of e to power j omega will be mod of cos of omega. Okay. Put the mod here. Okay. That will be the correct answer. If you remove the mod, this cos omega can go to negative, but since you are putting the mod here, it should not go to negative. And that's why that is the difference here, the cos omega and cos of mod of cos of omega. So this is wrong, this will be the right. Because here we need to find out the magnitude. Anyone has any doubt? Let me go to the next slide then. Okay, here a discrete time low pass filter frequency response is, okay. Here we are talking about the discrete time low pass filter, and here when you plot the discrete time low pass filter from minus pi to plus pi, this is how it is going to look like. Okay, some cutoff frequency. Okay. Now, but when you try to plot it from minus infinity to infinity, so as I told, this is going to be periodic. Okay, with period 2 pi. So here you'll see like this and like this. This side also you'll see like this, and here also you see like this. So this is pi, this is 3 pi, this is minus 3 pi. Now this is omega c. So this is going to repeat after 2 pi. So this will be minus omega c plus 2 pi. This will be plus omega c plus 2 pi. And this will be centered around 2 pi. Then there will be 4 pi and so on. This is how the low pass filter frequency response is going to look like in the frequency domain. Okay. So here this will be the correct answer, periodic with 2 pi. Okay. This aperiodic will be wrong, and periodic with response restricted to this. Okay, so this is also wrong because this is a its response will be there at this point also, from here to here. Its response will be there from here to here also. Its response will be there from here to here also. So this will be like periodic with 2 pi. Let me go to the next slide. Okay. If the jet transform is given in this form, what kind of filter is this? Okay. So whenever this kind of problem is given in the jet domain, you need to replace jet with e to power j omega and then find out what kind of filter is it. So h of e to power j omega will become alpha plus e to power minus j omega divided by 1 plus alpha e to power minus j omega. Okay. To find out what kind of filter is it, I need to take the magnitude and see how does it look like. So when I take the magnitude, I will just expand this. So this will become cos omega minus j sine omega, and denominator will be 1 plus alpha cos omega minus j alpha sine omega. Now let's take the magnitude. So it will become under root 1 plus cos omega square plus sine square omega divided by under root 1 plus alpha cos omega square plus alpha square sine square omega. Okay. Now if you solve this, this from this one you'll get 1 plus cos square omega plus 2 cos omega plus sine square omega. Okay, divided by, actually there is a there is alpha term, alpha square 2 alpha cos omega, and for this denominator you'll get 1 plus alpha square cos square omega plus 2 alpha cos omega plus sine square omega, alpha square. Now this alpha square I can write directly. Now this cos square omega plus sine square omega will become 1 plus 2 alpha cos omega. Okay. Now here we have 1 plus we have alpha square cos square omega, alpha square sine square omega. When you combine these two, you'll get alpha square plus 2 alpha cos omega. Okay. So if you see this numerator and denominator, they are same. So it is equal to 1. Okay. So what it means is that for all the frequency, the magnitude response is flat here. Okay. For all the frequency. And that means that this is all pass filter because it is passing the all the frequency. Okay. So generally, whenever you see the system which is in this kind of format, 1 plus z inverse, sorry, alpha plus z inverse, 1 plus alpha z inverse, this filter is always the all pass filter. Any doubt here? Let me go to the next slide then. Okay. So here again it is similar to what we have solved few slides back. So our impulse response is given, and based on this impulse response, we need to conclude what kind of filter is it. Okay. So to conclude about the filter, we need to find out what is the h of e to the power j omega and calculate its magnitude response and see how what kind of filter is it. Okay. So when you calculate the h of e to the power j omega, it will become 5 minus 7 e to the power minus j omega plus 7 e to the power minus 3 j omega, and then minus 5 e to the power, okay, minus 5 e to the power minus 4 j omega. Okay. Now this two term has 5, so I will take the 5 common. It will become 1 minus e to the power minus 4 j omega. And this two term has 7, so I will write it as a minus 7 and e to the power minus j omega minus e to the power minus 3 j omega. Okay. Now here this thing, just like we did few slides back, you can take something common such that it becomes some kind of cos or sine form. Okay. So take the e to the power minus 2 j omega common here. Okay. You'll get e to the power 2 j omega minus e to the power minus 2 j omega, then minus 7. Here also you can take something common such that it become that format. So here you can take again e to the power minus 2 j omega common. So it will become e to the power j omega minus e to the power minus j omega. Okay. Now you can divide it by 2, divide it by 2, and then multiply it by 2 and multiply it by 2. Okay. So you'll get 5 e to the power minus 2 j omega. This will become cos, sorry, not cos. It will be sine here. Sine 2 omega and minus 7 e to the power minus 2 j omega
That J should be
sine omega.
multiplied. Right?
There'll be 2, yeah, there'll be 2. Wait. So this will become 10 and this will become 14. Yeah. Okay. Now you can take e to the power minus 2 j omega common here. So once you take e to the power minus 2 j omega common, you will be left with sine 2 omega minus sine omega, and there is a 10 and 14 here.
So
Okay.
J term should be multiplied by
Which one?
J.
J also multiplied, sir.
J e to the power minus j.
Like multiply
2j
into
by
division.
2j into
Okay,
2j.
okay, it is 2j. Yeah, sorry, yeah, it is 2j. It is sine
Just like
j.
10, 14 and 10j and 14j, sir.
So this will be j here.
Yeah.
Okay. Someone was waiting in the lobby. Okay. Now we need to take the magnitude of this and then plot it. So once you take the magnitude, you can remove this term here, this completely. It will be simply the mod of this 2. So the mod of h of e to the power j omega will become mod of 10 sine 2 omega and then minus 14 sine of omega. Okay. So when you plot this, let's start. So when you put the omega equal to 0 here, you'll get 0. Okay. Because at omega equal to 0, the sine will be 0, both of them. Okay. Okay. Now when you let's see what happens when you put omega equal to pi here. Okay. Because we need to plot it from minus pi to pi. When you put omega equal to pi here, this term will be 0, again this term will be 0. Okay. So again at pi also this is 0 and this is 0. Okay. Only somewhere in the between it will go something like this. Okay. And it will be going something like this. Okay. So if you see this filter looks like a band pass filter. Okay. You can simply remove this low pass filter option because it is rejecting the DC. You can remove the high pass filter option because it is rejecting the this high frequency signal also. Next is the band stop and band pass filter. So band stop filter, it looks something like this. So minus pi to pi, it is just opposite of band pass. Okay. So band stop will have like it should pass the high and low both. Okay. But we know that it is not passing the low frequency as well as the high frequency. So this option will also go away, and you will be left with band pass filter. So when you plot this, this is how it is. This is not exactly, but it is something like this only. It is going to look like. So low frequency signal and high frequency signal will get suppressed because of the when you put omega equal to 0 and omega equal to pi, this is equal to 0. So this is equal to 0 at omega equal to 0 and pi. Okay. And because of that, this will go away. This is rejecting the DC as well as the high frequency, and it will pass only the somewhere the signal which is somewhere between 0 and the pi. So that's why it is mimicking the band pass filter response. Okay. Anyone has any doubt here? Okay. Okay, that's all we have for the today's class. Anyone has any doubt from the class, like from the beginning itself? You can ask the doubt.